Welcome back, students. We are finally going to begin into the field of statistical thermodynamics. What we're going to be doing is relating the past couple of lectures where we've come up with definitions for the Boltzmann's constant and the partition function and so on, and actually bring those into the bulk thermodynamic properties of the system. So a little bit of review before we get into the meat of today's lecture. The macroscopic properties of a system are determined by capital Q, which is the canonical partition function. This canonical partition function is related to the microscopic partition function, which is the lowercase q, the molecular partition function, in the following way for indistinguishable particles. So capital Q is equal to the lowercase q raised to the n, where n is the total number of particles divided by n factorial. This lowercase q, this molecular partition function, is based off of the quantum mechanical energy levels for molecules. In fact, the total partition function is equal to the product of the individual partition functions for all of the degrees of freedom, and we've derived what these are. Here's the expression for a diatomic molecule. For polyatomic molecules, it's more or less the same. We get more degrees of freedom, so it's a little bit more messy. So what we can do is, now that we know how to solve for the partition function for any degree of freedom, we can actually start to apply that and connect this canonical partition function to molecular systems. And that's what we'll do today. So today we'll be talking about the statistical definition of internal energy and constant volume heat capacity. These are two factors that we used a lot in basic thermodynamics, and we talked about the internal energy of the system, the heat capacity of systems. And we're going to see how internal energy and heat capacity are based off of the quantum mechanical degrees of freedom that the molecules that make up the system that contain them have. We will begin by considering the energy of a system. The total energy of an ensemble is simply equal to the number of ensemble units n times the average energy of each component of the ensemble. Remember, typically our ensemble components are going to be single molecules. So the total energy is based off of the number of molecules times the average energy of the molecule. We can rearrange this expression to say that the average energy of an individual part of an ensemble, which again is our molecule, is equal to the total energy divided by the number of particles. Again, this is just basically restating the same thing. What we can do from here is have a different expression for the total energy. The total energy is simply equal to the sum of the energy levels of all of the molecules times the number of molecules at each energy level. So if we have a 10-component system where one component is in the ground state and 9 of them are in the first excited state with 1 unit of energy, there is a total of 9 units of energy in that system. And then what we can do is we still have this capital N in there, the total number of particles. So from here, what do we do? In the past few lectures, we have been deriving expressions for A(n) over n. We said that A(n) over n, using the Boltzmann distribution, is simply equal to e to the minus beta epsilon n over the partition function Q. So we can substitute that in here and find that the average energy is in fact equal to the sum of the energy levels times e to the minus beta epsilon n over Q, and Q here is a constant, so we can pull it out of the sum, and it's 1 over Q times the sum of epsilon n e to the minus beta epsilon n. We can rewrite this in a more compact form by noting that the term in the sums looks quite a lot like the partition function itself. So recall that our partition function Q is equal to the sum over all of the n of e to the minus beta epsilon n. And what we have over here in our sum is e to the minus beta epsilon n, but that's multiplied by epsilon n. So we can note that the derivative of Q with respect to beta would be the sum over all of the n's of epsilon n e to the minus beta epsilon n, and this would be negative. So we can substitute this here, we can substitute dq d beta in for our term here. And what we end up with then is that the average energy is equal to 1 over q times negative dq d beta. And in some cases, we'll leave it like this. We can say that we have negative 1 over q dq d beta is the average energy of our molecules. And in other cases, it's a little bit more convenient to write it as the negative derivative of the natural log of q with respect to beta. So these are, in fact, equivalent. Plugging this back into our original equation up here, we can figure out that the total energy of a system is equal to n times the average energy, which we'll write as negative n times the derivative of the natural log of the microscopic partition function q with the derivative with respect to beta. In some cases, it's easier to calculate energy as a temperature derivative rather than a beta derivative. We can fix that pretty easily. So we can say that this is also equal to negative n times the derivative of the natural log of q with respect to temperature. And then we have to multiply that by dt d beta. And dt d beta, we can figure out what that is. So if we take the derivative of beta with respect to T, right, that is the temperature derivative of beta, which is 1 over kT. So that becomes negative 1 over kT squared. So that means that dt d beta is negative kT squared. So we can also write that our energy is equal to n kT squared times the temperature derivative of the natural log of q. In some cases, it's easier to do a beta derivative. In some cases, it's easier to do a temperature derivative. Just like we'll see in some cases, it's easier to take the derivative of the natural log of q, and in other cases, it's easier to take the derivative of q itself. And it just depends on the situation. All of these are equivalent, and sometimes the math is just easier. Here we have ended on an expression that suggests that the energy of a system will change when the temperature changes. A conclusion we are familiar with from basic thermodynamics like we were doing from the start of the semester. We can use this equation to determine the energy of a system based on the partition function. As an example, we can consider a system with only 2 available energy levels. So we can have a ground state, and we usually say this is at energy equal to 0, and we can have an excited state, and our energy here is maybe equal to h nu, the kind of light that needs to be absorbed to accomplish this transition. So we can calculate then the likelihood of being in either of these states. So our partition function q, right, q is equal to the sum. In this case, we're going from only 0 to 1 of e to the minus beta epsilon n, which is simply then e to the 0 plus e to the minus beta h nu, which is then 1 plus e to the minus beta h nu. We can take the derivative of this with respect to beta. So the derivative of q with respect to beta is going to be equal to negative h nu e to the minus beta h nu. So the total energy is equal to the number of particles times the average energy, which is then equal to negative n over q times dq d beta. And so in this case, we have nh nu e to the minus beta h nu over q, which is 1 plus e to the minus beta h nu. And it's often a little bit nicer if we divide e to the minus beta h nu from each term, which gives us nh nu over e to the beta h nu plus 1. And this is our function for energy. We'll go to the slides here and look at what happens to this function as temperature increases. Here we can see some plots of the function that we just described. These are the same plots, except for on this plot here, we're going from 0 to 1.5, and here we're going from 0 to 15, so it's just a longer window. What we can see is that at low temperatures, so at kT is, less than 0.5, maybe less than 0.2 h nu, the probability of observing a molecule in the excited state for our 2-state system here changes very little to not at all. Why is this the case? Because the energy that could be added at low temperatures, right? So if we're starting at zero energy and we're adding only a little bit, that's not enough to actually promote a molecule into this excited state. So we have very little change in the probability or the total energy, if we wanted to plot it that way, with respect to increasing the temperature at low temperatures. At high temperatures, the energy ceases to increase, and we get this plateau here. Whereas the plateau, well, note the plateau is happening at 0.5. Why is this the case? At very high temperatures, very high energy, the particles become equally likely to be at either energy level. So looking at this expression, what happens to beta h nu when a beta gets very small, which would happen at high temperatures, 1 over kT? Well, when 1 over kT gets small, e to the beta h nu gets small, which gets us 1/2. So the maximum probability we can ever actually observe at this highest energy level is 1/2. And this just comes right out of the math here. So at high energy, the high energy limit is not all of the particles being in the excited state, but it's all of the particles being equally spread out at every state possible, which in this case would be 50-50. If we had 3 energy levels, it would be 1/3, 1/3, 1/3, and so forth. So the total energy we can see actually maxes out at 0.5 quanta of energy times the number of particles in our system. The next thing we seek to do is to compare this energy that we've been calculating to some thermodynamic parameter. So what is the energy that we've been using here? We are building off of our previous discussions in which we are considering what we call the canonical ensemble. The canonical ensemble has a constant temperature, volume, and number of particles. Since the volume is constant, this energy that we've been calculating is identical to the internal energy of the system, which remember is easiest to calculate for constant volume parameters. The internal energy of the system, right, delta U was equal to the heat at constant volume, and we can also write this as the internal energy minus some 0 point of internal energy, some standard internal energy is equal to the heat. By convention, this U naught here, which is the energy of the system at 0 Kelvin, is 0. Therefore, the energy of the system at temperature, any temperature T, is always the internal energy if this comparison at 0 Kelvin is 0. So what we have is that the internal energy of our system is equal to negative n times the derivative of the natural log of the microscopic partition function Q with respect to beta. And we can also say then that this is equal to the negative partial derivative with respect to the natural log of the canonical partition function with respect to beta at constant V. How have we done this? We made this last equality by recognizing the relationship between our canonical partition function, capital Q, and our molecular partition function, the lowercase q. So if our canonical partition function, capital Q, is equal to Q raised to the n over n factorial, then the natural log of Q is equal to the natural log of Q to the n over n factorial, which is equal to n natural log of Q minus the natural log of n factorial. If we take this derivative with respect to beta, so the derivative of the natural log of Q with respect to beta, we get the derivative with respect to beta of n natural log of Q minus the derivative with respect to beta of natural log of n factorial. N factorial is a constant, so this term is not beta dependent and it's 0. And the remaining term is simply n times the derivative of the natural log of Q with respect to beta. So we can go ahead and substitute that in for the following equality above. Now, what is the internal energy of a system of a molecule? From the above equations, we can see that the internal energy is simply equal to the negative n, which n is the number of particles, again, times the derivative of the natural log of Q with respect to beta. we can substitute in what the molecular partition function Q is, right? The molecular partition function is simply the product of the translational, rotational, vibrational, and electronic partition functions. And what we can do with this, using log properties, we can say that this is equal to negative n times the derivative of the natural log of the translational partition function with respect to beta, plus the derivative of the natural log of the rotational partition function with respect to beta, and then continue on for all of our partition functions. We also have the vibrational and the electronic. And all of these are at constant volume scenarios. That's our definition of our canonical ensemble. And we can look at this and say, well, if I'm taking the derivative of the natural log of the translational partition function with respect to beta times negative n, that's simply the translational internal energy, and then we can have the rotational, the vibrational, and the electronic. So to figure out what the internal energy of a system is in any temperature based on quantum mechanics, we simply have to evaluate the derivative of the natural log of the various microscopic partition functions for each molecular degree of freedom, and then add those together. We are able to evaluate the beta derivative of each degree of freedom individually and add them together to determine the total internal energy of our system. So like before, we will start off with translation. Recall that the translational partition function is as follows. We defined it as the volume over the thermal wavelength cubed, which is this capital lambda. And to put that into more simple terms or more common terms, that is 2 pi times the mass of the particle over h squared beta raised to the 3/2 times the volume. Now we have to take the derivative of this with respect to beta. It can look kind of nasty, but remember what we're actually doing, and it's much easier, is to take the derivative of the natural log of this with respect to beta. So our internal energy for translation is equal to negative n times the derivative of the natural log of the partition function with respect to beta. Now, this might look challenging, but it's actually simpler than you imagine because of log properties. So what we can do is say that our internal energy for translation is equal to negative n times the derivative with respect to beta of the natural log of everything that is not beta. In this case, that's 2 pi m over h squared to the 3/2 times the volume. And then we have our beta term left over, and I'm going to use log properties again to write that as negative derivative with respect to beta of 3/2 times the natural log of beta. And again, this is just using the log properties here. Now, why have I done it this way? Well, what's the derivative of a whole bunch of constants that don't depend on beta with respect to beta? It's 0. So this whole term is simply equal to 0. And what we have then is that the internal energy with respect to translation is simply equal to, in this case, positive n times the derivative with respect to beta of 3/2 natural log of beta. And the 3/2 is, of course, a constant. We can pull that out. So we have 3/2 n times the derivative with respect to beta of the natural log of beta. And the derivative of beta of the natural log of beta with respect to beta is 1 over beta. So this gives us 3/2 n over beta. Beta is simply kT, so it gives us 3/2 n kT. And you may remember this, but n is the number of particles, and k is Boltzmann's constant. And so we can relate nk, the number of particles, times Boltzmann's constant, which is the energy per Kelvin per molecule, to nr. So capital NK is the same as lowercase nr. The number of moles we're talking about times the molar gas constant here, because the Boltzmann's constant is simply the gas constant divided by Avogadro's number. So what this gives us is that the internal energy based on translation is simply 3/2 nRT. Now, what does this look like? Well, how do we used to calculate internal energy? We used to say that the change in internal energy was equal to the heat capacity, the molar heat capacity, times delta T, which gave us, if we used a monatomic gas, the molar heat capacity was 3/2 nR delta T. And in this case, we're assuming that our initial temperature is 0, so delta T simply becomes T. And despite using quantum mechanics, we came to the same conclusion we did using thermodynamics. So that shows us the power of this statistical thermodynamics process. What about rotation? Well, the rotational energy levels for a diatomic molecule was as follows. So, and this is necessarily a linear molecule, which is most commonly diatomic. So our Q sub R was equal to 1 over sigma, which is the symmetry coefficient there, times beta HCB, where B is the rotational constant. Just like before, we can calculate the energy for rotation, and that is equal to -n times the derivative of the natural log of Q sub R with respect to beta at constant volume. And we can do the same thing. So we can say this is equal to -n times the derivative with respect to beta of the natural log of 1 over sigma HCB, and then minus the derivative of the natural log of beta with respect to beta. Again, this whole term is 0, and what we end up with is that this is equal to n times the derivative with respect to beta of the natural log of beta, which in this case is n over beta, or nkt, or nRT. So for a diatomic molecule that has 2 rotational degrees of freedom, the contribution from the rotational energy levels to the total energy is simply nRT. For nonlinear molecules, you might remember that Q sub R is a little bit different, and Q sub R for nonlinear molecules was the square root of pi over sigma times 1 over beta HC to the 3/2 times 1 over 3 different rotational constants, depending on the moments of inertia of the molecule. And you'll see here, what do we have? Well, here we have beta to the -3/2. So you probably won't be surprised that, just like translation, if we were to do this nonlinear molecule, we would end with UR being 3/2 nRT. Vibrations were a little more complicated since the vibrational energy levels are not equally accessed, unlike translation and rotation for most molecules. We've already seen that we can determine the vibrational partition function using a series identity. So what we have is QV, the vibrational partition function, being 1 over 1 minus e to the minus beta HC nu, and here we'll write that as 1 minus e to the minus beta HC nu raised to the -1. In this case, to get the total energy for vibration, it's actually easier to take the derivative of this, not the derivative of the natural log of this. So we'll say that U sub B is equal to -n over Q sub B times the derivative of Q sub B with respect to beta. So again, this is just a derivative. It's a little bit more cumbersome than the last ones, but it's not anything that you can't do. So we can go ahead and evaluate this. We'll get -n over Q sub V, and the derivative of Q sub V here with respect to beta, we can simply evaluate that using the chain rule. So we'll get 1 minus e to the minus beta HC nu to the -2, and then multiply that by the derivative of the inside, which is minus HC nu times e to the minus beta HC nu. And so if we put this together, what we end up with is NHC nu e to the minus beta HC nu divided by 1 minus e to the minus beta HC nu. And what we can do, just like we did a little bit before, is divide each side of this equation by e to the minus beta HC nu. And what that gives us is NHC nu e to the beta HC nu -1. And this is our expression for how vibrational degrees of freedom contribute to the total energy. The amount of energy contributed for vibration is heavily dependent on the temperature. So in the high temperature limit, we can use the approximation So at high T's, e to the beta hc nu is approximately 1 plus beta hc nu. And so what that gets us at high temperature would be n hc nu over beta hc nu, and then we would have plus 1 minus 1, those would cancel out. And then we'd cancel out our hc nus, which would give us n over beta, which is nkt, which is nRT. And we've seen this before. But for non-high temperatures, we actually have to evaluate this expression. And it's not even. So different temperatures might contribute some, little, or none energy to the total energy if we're not very near temperatures that can access higher energy level vibrational states. For electronic degrees of freedom, we have previously noted that the electronic energy levels are spaced very far apart. This caused the electronic partition function to tend to be only the degeneracy of the ground state. So we could say that QE is equal to G naught, where G naught is simply a constant. The contribution to the internal energy then is negative n times the derivative of the natural log of a constant G naught with respect to beta. G naught doesn't depend on beta at all since it's a constant. So this is almost always 0 as long as there's no significant occupation of higher level electronic states, which is not always true, but it's often true. Putting all of these together, we obtain the following results for a diatomic molecule. So the total internal energy U is equal to, like we said before, UT plus UR plus UV plus UE, and we solve for all of these individually. So UT was 3/2 nRT. For a diatomic molecule, UR was nRT, and then the vibration was NHC nu over e to the beta hc nu minus 1, and then electronic contribution was 0. So putting all of these together, we have 5/2 nRT plus NHC nu e to the beta hc nu minus 1. And with this, we can calculate our total energy at any temperature for a diatomic molecule. For polyatomic molecules, there'll be more vibrational degrees of freedom. And the rotational contribution will be 3/2 nRT. This also assumes that the rotational energy levels are approximately continuous, which is again true for most, but not all molecules, and that only the electronic ground state is significantly occupied. We can then in turn define the heat capacity. So remember, and we wrote this a little bit earlier, that we used to calculate delta U by using the heat capacity times delta T. So what that means is that the heat capacity is equal to delta U over delta T, or the derivative of the internal energy with respect to temperature at constant volume. We can turn this around, instead of taking a temperature derivative, take a beta derivative, and say that this is also equal to negative K beta squared times the partial derivative of internal energy with respect to beta at constant volume. Since we have already described internal energy based on the quantum mechanical energy levels, we can simply take the temperature derivative or the beta derivative to find out what the heat capacity is. Since the translational and rotational energy levels are usually continually accessed, the internal energy for only translation and rotation was 5/2 nRT, which means that the heat capacity of that, which is equal to du dt, is simply 5/2 nR for a rotating diatomic molecule. And we could say then that the molar heat capacity, right, CVM, which is CV divided by moles, is then only equal to 5/2 R. So compare this results to our first lab we did. Remember the heat capacity of nitrogen, N2, was basically 5/2 R, a diatomic molecule. And this is exactly why, because the vibrational levels were not accessed very much. If we have vibrational levels accessed, we also have to evaluate the contribution to the heat capacity for vibration. So the contribution to the heat capacity for vibration is equal to negative KB squared times the partial derivative of the vibrational internal energy with respect to beta. Again, this is a little bit nasty, but something that we can pretty easily do. So it says negative k beta squared times the derivative with respect to beta of nhc nu times e to the beta hc nu minus 1. And if you go ahead and do this derivative, you get a funky looking equation that we used in lab 1, that is nk beta squared hc nu squared times e to the beta hc nu over e to the beta hc nu minus 1 squared. So as weird as this equation looks, we can use this to calculate the contribution to the heat capacity based on vibrational energy levels. And we did this in lab 1. For nitrogen, beta was very different. So KT was very much lower than HC nu, which made this overall contribution be almost 0. But for carbon dioxide, which is also a linear molecule, there were some low-lying levels of degrees of freedom that actually had some access. And what that was, it was approximately, at the end of the day, we go back and do these calculations, that the contribution to the heat capacity for carbon dioxide based on vibration was approximately R, or I suppose we could say NR, if we're not talking about molar heat capacity. So sometimes vibrational energy levels can be low enough in energy that they actually do contribute to the overall heat capacity. And for molecules that don't just have one vibrational degree of freedom, so for polyatomic molecules, the heat capacity is simply the sum of all the contributions from each vibrational mode. Since there is no contribution to the internal energy from the electronic degrees of freedom, for the most part, there is also no contribution to the heat capacity. So the heat capacity for the electronic degrees of freedom is 0. In the next lecture, we will continue to investigate these sorts of things. We'll go look into the entropy, free energy, and equilibrium constant and see how we can explain those based only on quantum mechanics.